Exams back for you today, so if I get too excited talking about something, remind me there's about 3-4 minutes to spare at the end of class, and I'll stop and return those. Also, if you have any questions or concerns, I can uncharacteristically stay after class today, so if you have any questions, I'm happy to address those, homework or whatever. I think there's another class that meets in here, so we'll have to migrate back to my office. But so that's kind of the announcements for today. Other than that, you have homework 7 on deck, which I've already finished, and we're moving well into homework 8, so that when homework 7, when that deadline comes up, I'll be able to post a new homework for you that you can get started on right away. And I'm looking at a second exam after homework number 9. So the homeworks 8 and 9 stretch out a little bit, but I'll give the official 2-week announce as usual. And at this point, I have no reason to think it won't be the week that's projected on the syllabus. Okay, any quick administrative or logistical questions before I get started? Okay, so we're talking about momentum. Momentum is the conserved quantity that is born from Newton's third law. So if we have two objects interacting, the forces they exert on each other are equal and opposite. That's Newton's third law. And if we substitute in that the force on an object changes its momentum, and we cancel out the common contact time, they'll exert forces on each other for a common amount of time, and then rearrange their deltas, group the initial stuff on one side and the final on the other, we find that there is a conserved quantity. And that's the momentum of a system. So when you have a system of multiple objects, they can exert forces on each other to their heart's content, but that will only result in momentum being taken from one and given to another, but the overall will not change. So the upshot of this is that if there is no net external force on a system, you can be guaranteed that the momentum of the system is conserved. They can have any number of internal interactions of unknown duration and an unknown force. It doesn't matter, because all of those will obey Newton's third law. And so here I've drawn a system of 1, 2, 3, 4, 5, 6 particles. They can crash and bang into each other as much as you want. But if we can be fairly certain that we can group these things into their own system, which is relatively isolated from the outside world. So they can bang into each other as much as they like, but there is no net force from the outside. So we have an approximately isolated system. There's no net force coming in from the outside, no net external force. Then we can be guaranteed that even if all of these crash into each other and none of their individual momenta are the same after some large number of interactions as they were at the beginning, the sum total of those momentum will be the same. Okay? So that's the beauty of momentum. An example would be, for instance, an enclosed container of gas, right? You can have a large number of gas particles all colliding into each other. You don't want to be keeping track of all of those collisions. You just want to be able to say that there's some conserved quantity, so sometime later you can count it up and get the same value. And so again, because all of those interactions obey Newton's third law, that quantity that's conserved is momentum. It is a vector quantity, so you do have to now keep track of vectors. Saw on a few people's exams, still haven't gotten the hang of components, about this idea that you need to break things up into 2 directions. That will haunt you forever, or at least as long as you are in physics 1 and 2. You've got to get the hang of that, okay? Resolving things into components. Right off the bat here, I'm going to jump in with a 2-dimensional example of a momentum conserving collision. And so let's go ahead and do that. Oh, and I guess one thing I want to even do first, before I even do that, we can take an interesting system that we've looked at previously. This was the child and parent pushing off each other on the ice. You did this at, I think, the end of homework 4 or 5 or something like that. you basically found the forces they exerted on each other were equal and opposite, but their accelerations were not equal, right? Child has less mass, so had more acceleration. Let's couch it in terms of momentum. Well, I pick my system as both of them. I guess I'll call them A and B. And that system is relatively isolated from the outside world. There's no net external force. The reason why? Well, if they're on ice, there's no friction on their feet, and it's relatively flat, so the normal force and gravity cancel. So if I pick both of them to be my system, then the force they exert on each other is internal, but won't change the momentum of the system. So let's take a look at the momentum of the system initially. If they're both just standing there, what's the momentum of each one? 0. Momentum is just mass times velocity. They don't have any velocity. So the system has no momentum. Afterwards, they push off each other. So that one goes this way, one goes this way. And of course, the force that they exert on each other doesn't last forever. It only lasts when they can reach each other. After that, they have some final velocity, VA final and VB final. And once they've parted ways, if there's no friction to stop them, Newton's first law tells us they'll maintain that velocity forever. Now the velocities are not equal and opposite. And we learned that, of course, if they don't accelerate equally during the time that they're touching, they're not going to achieve the same final velocity. What is equal and opposite is their final momentum. Because their final momenta must add up to 0, just like it was at the beginning. There was no net outside force, so the momentum is the system overall must still be 0. And what that means is that they have equal and opposite final momenta. So you can see that momentum is a really fundamental thing. When two people push off each other, it's not their velocities that are equal and opposite as they go further away from each other, it's the momenta. Which means that if mass A is smaller, the final velocity is larger. And if B's mass is bigger, its final velocity is smaller. That's entirely consistent with what we found about the accelerations. But this allows us to very quickly jump to knowing what is their final velocity. If we know, for instance, the relative mass, so we know both masses and we know one of the final velocities, we can very quickly find out what the other one is. We don't have to use that final velocity to work backwards to figure out what the acceleration was and the force was, and then take the equal force and put it on the other one. We can just immediately jump to what is the other final velocity. Okay? So that would be an example of this calculation. Don't want to kind of do the whole thing out, but you get the general gist. Are there any questions on this before I move on to a two-dimensional version? Okay, so let's do a two-dimensional version. You'll have one of these. The hardest part of this problem is not the physics, it's the math. It gets some annoying kind of things that you have to bookkeep, but I'm going to set up, this is a top view of a frictionless table. So the same playing field that's very common, it practically screams momentum conservation. It's a frictionless horizontal table. That's the way you can get this system to be relatively isolated from the outside world, right? No friction, and then normal force and gravity cancel on a horizontal surface. So this is my playing field where I can isolate a system basically from the outside world and just let things happen internally. And the reason I draw it from the top view is because now the collision is not going to be head-on, it's going to be glancing, so it's going to look like this. Here's A coming in to collide with B. And that's not my poor drawing. A is intended to look like it's going to come in for a glancing collision with B if this is the initial state of the system, the final state is going to look like this. If you've played any pool, you know about this kind of thing. This is the final state of the system, something like this. The collision they have is going to be internal. Let me give you some values. Let's say that the mass of A is 1 kilogram, and the mass of B is 2 kilograms. Let me say that A comes in at 5 meters per second, and B is at rest. And then B is found to go out of the collision at 2 meters per second at 45 degrees. And my question is going to be, how fast and at what angle does A emerge from this collision? It's going to turn out that both of those have to be spoken for. If momentum is to be conserved, then those two values are locked down. So there's a bunch of annoying bookkeeping that requires you to be organized in terms of tackling the math. But as far as the setup goes, here's how I'm going to think of it. In the x direction, what's going on? Initially, I have A is going to the side, and that's it. I'm not going to draw B because B has nothing going on. So basically what that means, I guess I should mark my axes here. X is going to be to the right, Y is going to be like that. So what I find is in the x direction, my momentum of the system in the x direction is positive. I have positive x momentum. I guess let me go ahead and write it out over here. So momentum of my system is conserved. Let's unfurl this out to 32 subscripts. Okay, there are going to be 32 subscripts in this equation. Okay, if the momentum of the system is conserved, the momentum of A plus momentum of B has to be conserved. So they trade momentum amongst each other when they collide, but the sum total must remain the same. So that means that MABA plus MBVB is a constant. That's momentum, right? M times V. Now, this is a vector equation, so any vector equation can be split up into x and y components. We've done this plenty, right? We took our Fnet equals MA, and of course split it up into our classic Fnet x equals MAX, Fnet y equals MAY. So if the x and y axes are independent, then whatever happens in the x, as far as the net force, will cause the x acceleration. Y net force causes y acceleration. So same thing here. Any vector equation can be split up into equations of its components. So what do we have? We have m, and let me do the subscripts, not all consecutively, because if you're not practiced in writing them, then you're going to find that you quickly start to get mixed up. So let's do first A, B, A, B. Okay, so we got to keep track of A and B. That's my system. This is my initial side. This is my final side. Notice that the masses only need identifying by A or B. The masses don't change upon collision. It's only the velocities that may, right? So only the velocities need initial or final. And then finally, this will be my x equation. X, 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 x. So the roadmap for subscripts, I have A, I have B, I have A, I have B. This side is the initial side. This side is the final side. And finally, this entire equation is the x equation. So you have this kind of cascading waterfall of subscripts going off the velocity, which is necessary. Velocity of what? A or B? Is it initially or finally, before or after collision? Is it in the x or y direction? So that's why you need 16 subscripts. And of course, the y equation gives you 16 more for a total of 32. So let's take a look. This x velocity, well, the initial velocity in the x direction is 5 meters per second, and the other is 0, right? So all the momentum in the x direction is carried in by mass A to begin with. Afterwards, it's carried away by both A and B. You can see that both A and B have horizontal components afterwards. So afterwards, A and B both carry that momentum away. So that'll give you one equation. Of course, these will be both positive x components. And I'll leave the SOHCAHTOA to you. Now, one of the things that you can note right away is that if B is going to carry away some of the horizontal momentum afterwards, A has to lose some, right? So basically A shares. A is going to give some of its momentum to B. So A's momentum alone is going to decrease so that it gives some to B, but the total remains the same. So I can say for sure that this is going to be less than 5 meters per second. A has to slow down. What slowed it down, by the way? Why did A slow down? What's the only way that something can slow down? Not friction. There's no friction on the surface. It collided with B, right? It felt the force from B. Now that force, I guess I can draw while they're colliding, like that, A, B. The force is probably like this. Force on A from B, like so. It's going to be like that simply because the normal force, which is really where this collision is coming from, that's how they're contacting each other, right? That's directly away from the surface of contact. So I do want to point out that this force here does have a component against A's initial motion, right? There is a component of that force that slowed it down. And of course, likewise, you can see that this other force, there's a forward component which causes, of course, what causes B to pick up from rest. B starts moving to the right because it felt the force which in part was to the right, so instead of being at rest, now it's moving to the right. Okay? Now I'm just pointing this out because you might be curious as to how they exerted forces on each other, but it's not really necessary because you can just make sure that the momentum is all there, right? So all the momentum is carried in the x direction by A. This is 0. And what we're just basically saying over here is we need to see all of it on the way out, too. So that'll give you one equation. And the other equation is just replacing the x's with y's. Don't want to write the whole thing out again. Let's talk about that. The most important thing is get the concepts. You can crunch through the math at home. So initially, what's going on with the y direction? How much momentum do we have in the y direction? We don't have any. Nothing's happening in the y direction. So nothing. So how much momentum must be in the y direction afterwards? Also 0. Momentum has to be conserved. Well, how is that going to be possible when they are both obviously now have motion in that direction? So I can draw those components over here. How can those two add up to 0 still? Well, momentum is a vector. There's going to be a positive momentum for this one and a negative for this. And a positive and a negative can add up to 0 still. It's basically this all over again. So this ice skater, there was no momentum at all, and then equal and opposite momentum at the end. That's basically incorporated into the y direction of this two-dimensional collision. Okay, so these are equal and opposite momenta. And we'd have a second equation. Now again, if you're curious how two things can suddenly both start moving in the y direction, even though nothing was happening in the y direction, it's because of that glancing collision, right? So this glancing collision, both of these forces also have components. This one has a component this way, this one has a component that way. So that's what initiated the motion in the y direction, was this collision force that they had, which was along a diagonal. But again, we don't really need to worry about that detail. You don't really need to think about this too much, because you're just going to have a second equation where you make sure that the momentum is all there. In the y direction, you have no momentum at all to start with, and that's why the two at the end have to be equal and opposite. So what you do is you laboriously do all your SOHCAHTOA, all your sines and cosines, make sure you put your plus and minuses appropriately, and you'll get two equations, and two equations you can always solve for two unknowns. In this case, they happen to be the final speed and angle. So, your classic two equations, momentum in the x, momentum in the y, and you solve for any two unknowns. It doesn't really matter what they are. You can't get too fixated on what is left out, because it could be any two things involved. It doesn't really matter. And I'm just going to tell you what the answer is. Try this at home. Make sure you can get these results. If you don't get exactly these, it might be round off, but if you get something significantly off, let me know. The final speed is cut off on this. Angle's 52 degrees, and what is the size of it? I'm gonna have a calculator real quick. Oh, there it is. I think it's around 3.6. So try it yourself at home and make sure you can get that. So the principles are simple. You're making sure that the momentum is conserved in the x and y directions. That'll produce two equations. They may be kind of knotty and everything's intertwined. Like, you're going to have to unravel that knot and figure out what are the two things that are left out. Okay? Make sure you assign your components. Everything's got to be plus x, y, plus and minus, whoops, etc. Any questions on that? Okay, so that's basically momentum conservation. That's the fundamental idea. You want to have a system that you can somehow earmark into an inside and outside. You want to take everything included in your system if they're interacting in some way, and then you want to have a relatively isolated thing so that you can approximate that no net force comes in from outside. So all the forces of significance are on the inside, and those trade momentum of within the system not change the total. Now I should mention, how isolated can you truly get something? Well, of course, you can't really truly isolate something, so you can use this when the net force external is approximately 0. Now, approximately 0 is like, okay, well, what does that mean? How close to 0 is okay? Well, here's one way you can think of it. You can approximate this as 0 if the internal forces are much, much greater than the external forces, okay? That's a symbol that is used in physics sometimes. When you have two inequalities, it means you really mean it, okay? So not that the internal force is just greater, but much, much greater. So basically, the internal forces are the big action. The external forces are so small in comparison, you're neglecting them. It makes them look bad. I've heard it said that the definition of a collision is this. A collision, by definition, is a violent event. It's a big thing that happens between two or more objects, and the outside world is a relatively minor distraction, right? So I've even heard it said that, by definition, if you call it a collision, momentum conservation can be applied to it for reasonable results.